Okay, so let's have a look now at the hydrolysis of polyamides. So just like when we looked at hydrolysis of our polyesters, we're going to carry this out either using hot aqueous acid or hot aqueous alkali. I'm going to start off, I've got a section of a polymer chain here, and I want to first of all identify each of those amide linkages, in biology peptide linkages, that we can see here. And there's a few of them, so I've got more than one repeating unit. So I'm going to bracket this off to show where one repeating unit is. Okay, and the alkaline hydrolysis of this is going to use sodium hydroxide in the presence of water to cleave that amide link. So because I've got basic conditions, I would perhaps have formed a dicarboxylic acid, but I'm going to form instead a carboxylate salt. Beautifully drawn hexagons. As long as it's clear what it is, it doesn't matter. So the hydrogens that would have been here in a dicarboxylic acid are going to neutralise the OH from the sodium hydroxide that's present. So that forms more water and it's going to leave us with the sodium salt. And then I've got here the makings of a diamine, and that's going to react with some of the hydrogen that's present to form my diamine. Oh, you can't quite see the end of that. Can I move it so you can? Let's pop it here instead. There you go. So we get the diamine produced as well. So hydrolysis of polyamide using hot aqueous sodium hydroxide, we're going to make a carboxylate salt and a diamine. Let's have a look next at what happens if I use acid hydrolysis. So with acid hydrolysis, we're going to get slightly different products made. This is the one that's often slightly trickier when it comes up in synthesis or problem solving measures. So before, when we used the base hydrolysis, our dicarboxylic acid neutralised the OH that was present and gave us a sodium salt. This time we've got plenty of H plus present, so we're going to form our dicarboxylic acid. Aim for the neat hexagons. But now this presence of H plus, I would have formed a diamine with NH2, but now I'm going to form, because the amine is a base, the lone pair on the nitrogen is going to be able to hold on to another H plus. So instead, we're going to have this charged amine that's produced with each lone pair on the nitrogen holding on to additional hydrogens. Remember, just as with our polyesters, depending on the number of repeating units you've got is going to depend on the number of moles of water and the number of moles of each of these that you produce. So if we're told that it's N lots of repeating units, then we're going to need N moles of our dicarboxylic acid and N moles of our diamine. Okay, I'm going to write you a couple of examples for you to predict for me the outcomes with the alkaline hydrolysis and the acid hydrolysis. Let's see how we get on. Okay, so there's two sections of polymer chain for you to have a look at, and I'd like you to predict the products of acid hydrolysis and alkaline hydrolysis, please. Pause here while you have a go at that, and then I'll show you my workings in the next section. Okay, so hopefully you've had a go at that. I'm going to start off with my base hydrolysis first. So we're going to use sodium hydroxide in the presence of water. We might describe this as hot aqueous sodium hydroxide. I'm going to look at my molecule for everywhere I've got an amide link that can be cleaved, and that's going to help me to work out where my repeating unit is, and to then figure out what my molecules are going to be that I'm going to produce. So this is under basic conditions. So that means where I might have formed a dicarboxylic acid, instead I'm going to form my sodium salt. Either don't use charges at all, or remember your O minus Na plus, don't mix and match. And then I'm also going to form, under those basic conditions, a diamine. So I don't have to worry that there's other functional groups here at the moment, because in phenol that's not going to behave as an acid under these circumstances. So I'm just going to make my diamine and my dicarboxylate salt. That's the alkaline hydrolysis of that polyamide. Let's look at the acid hydrolysis. So in the presence of hot aqueous acid, that's going to have an impact on my diamine. I'm still going to get my dicarboxylic acid formed, so make sure that's got its clear OH. And then my amine acts as a proton acceptor, and I get this. Produced, which, because we've got an extra hydrogen on each of those, needs its two positive charges. So that's the acid hydrolysis of this polyamide. Let's have a look at example 2. So just as before, I want to have a look and see if I can find those amide linkages and work out what my repeating unit is going to be. So I've got one here and a second here, and I seem to have some overlap between some of these CH2 groups here. Now, maybe more for me, it's not necessarily obvious at which level that repeating unit is, so I'm going to mark it off as, just leaving it as that, as if that is one whole molecule. So that would, in fact, although those are the ester linkages, that would make my repeating unit something like this, okay, if I was going to describe the whole polymer. So as we have with previous examples, let's start off with our alkaline hydrolysis first. So hot aqueous alkali is going to give me, rather than a dicarboxylic acid, we're going to make the sodium carboxylate salt. So I'm going to be copying this molecule from here and then reading round in a banner. So CH2, CH2, CH2. Make sure your sodium and your oxygen are the right way around. And then I've also got my diamine that's going to be produced. So, spot the other error. H's missed off there and there. Get a bit overexcited sometimes. Okay, and that's my diamine. So for every N lot of this that's going to be hydrolyzed, I need N moles of water, and I'm going to be producing these two molecules, the dicarboxylate salt and the diamine. Let's look at what happens with acid hydrolysis. Okay, so with then my hot aqueous acid, I'm going to get the production of my dicarboxylic acid. And just like I did before, I'm going to start copying my chain from here and then follow it round in a circle. To form my dicarboxylic acid. And then I'm going to take my diamine, and remember that this is going to act as a proton acceptor. Okay, and so in acid conditions, this is going to be the diamine that I produce, and it's going to be a salt with the additional protons added. So if you've got any questions, shout. Hopefully we can look at some exam questions and put some of this into practice. Well done.